Okay, hello everyone. I would like to discuss pressure transient analysis using type curves. And that will be our lecture 6. Up to this point, we have illustrated the use of conventional semi-log plots. And you've seen how to analyze data in the middle time region, that is data that fall into the infinite acting radial flow period. However, this approach has some drawbacks, and that's one of the things we like to address in this lecture and the next. So traditional well tests had to be sufficiently long to overcome both well burst storage and skin effects. And why this was important is so that the straight line portion on the semi-log graph would be identifiable. Apart from needing to flow the wells sufficiently for a sufficiently long enough time so that the straight line would be identified, in some tests, more than one apparent straight line can be identified from the test data. And in such scenarios, analysts found it difficult to decide which one is the straight line portion representing infinite acting radial flow. In addition, depending on the choice of your scales, what is actually curved may appear straight, So to overcome these difficulties, other methods of analysis were developed. And in 1970, the type curve analysis approach was introduced by Agual et al. And since then, it has been used in conjunction with the same conventional semi-log plots. So what's a type curve? A type curve is a graphical representation of the theoretical solutions to, be it transient flow or pseudo-steady state flow equations. They are usually presented in terms of dimensionless variables. And I think that's one key point, rather than real variables like we've been dealing with. So instead of pressure, time, radius, well burst storage, instead you now have dimensionless pressure, dimensionless time, dimensionless radius, and dimensionless well burst storage. The type curve analysis consists of finding the theoretical type curve that matches the actual response from a test well and the reservoir when subjected to changes in production rates of pressure. Of course, we know for pressure transient analysis, we're looking at how pressure changes as you produce at a constant rate. The match can be found graphically and usually by physically imposing or superimposing a graph of the actual pressure test data on a graph of type curves, and then you try to find out or search for the type curve that provides the best match. So reservoir and well properties such as permeability and skin can then be calculated from the dimensionless pressure parameters, defining that curve. And I will illustrate this in this video. Now, because type curves are plots of theoretical solutions to the flow equations, they can be generated for virtually any kind of reservoir model for which a general solution exists. To apply the type curve correctly, you must appreciate the underlying assumptions used in developing the type curve. Furthermore, those assumptions must accurately model the reservoir or reservoir well conditions being analyzed. So the first point there brings to highlight the advantage of using the type curves as against the conventional analysis, because using the type curves represent different theoretical solutions. Once you can obtain an analytical solution to a particular diffusivity equation, it can be, type curves can be produced for that reservoir system, and then all you need to do is to superimpose your own test data on the type curve and look for a match. For a given period of the test, the change in pressure, that's delta P, is plotted on log scales versus the elapsed change in time. So you see, we've moved from the plot of pressure against the log of time, of course, so pressure on time on the semi-log graph. And now we're talking about the log scale. The log analysis is a global approach as opposed to the straight line methods. So as opposed to the straight line methods, that's the use of like the semi-log graph, the log analysis makes use of the whole data set. You know, you're not just looking for the straight line portion. The whole data set is used in type curve matching. By comparing the log data plot to a set of theoretical curves, the model that best describes the pressure response is defined. And when we talk about model, we're talking about the analytical solution that best represents the well reservoir system that we're working with. These curves are expressed in dimensionless terms, and as I mentioned earlier, because the pressure response becomes independent of the physical parameter, the magnitude of the physical parameters. And I think it's what I'd like you to, some things I'd like you to take note of here is for the type curves, you're plotting your test data on a log scale. And again, you are looking for a match to a set of theoretical curves that have been prepared or in form of graphical solutions. So I'd like you to just take note of this. Now, you recall that much earlier in the course, I gave a number of dimensionless terms. So equation D25 is the equation for dimensionless pressure. Of course, you see that there's usually a linear relationship between the dimensionless term and the dimensional term. Now, if you take the logarithm of both sides, both the left and the right-hand side, you would see that the log of dimensionless pressure is equal to the log of the change in reservoir pressure plus the log of this term. That's equation D55. So for a constant flow rate, the above equation indicates that the logarithm of dimensionless pressure drop will differ from the logarithm of the actual pressure drop by a constant amount. And that's what you can see from here. So this just shows that the logarithm of the pressure drop would only be if the logarithm of the pressure drop is plotted in a similar scale to the logarithm to dimensionless pressure, there will only be a shift, which is quantified by this shaded portion. And similarly, you can do the same thing for dimensionless time. This is the equation D30 for dimensionless time. You take the logarithm of both sides. You would give you D54, which shows you that the logarithm of dimensionless time to the actual time would differ by this constant amount. So hence we have a graph of the log of P and T. This is actual test pressure versus actual test time, which will be identically shaped to the graph of dimensionless pressure to dimensionless time, even though there will be a shift in, for this is the shift in the pressure curve, and this is the shift, what I mean, this is the shift in dimensionless pressure, and this is the shift on a time basis. So this is a shift vertically representing the for pressure, and this is for time. So it says not only, the important thing is that on a log-log scale, the plots of the dimensionless variables, pressure and time, is identical to the plot for dimensional pressures, dimensional variables, pressure and time. The only thing is that there would be a shift by these quantities. So not only do these curves have the same shape, but if they are moved relative to each other until they coincide or match, the vertical and horizontal displacements required to achieve the match are related by equations D55 and D56. I will demonstrate this in an example to bring the concept home. Once these constants are determined from the vertical and horizontal displacements, it is possible to estimate reservoir properties such as permeability and porosity. Now, so these are the four most common type curves which are used for the analysis for pressure transient analysis. And I'll just run through the four of them. The inherent assumption is that the formation is homogeneous, of course, and then it's a homogeneous acting formation producing slightly compressible fluids. Of course, we know that our reservoirs are not homogeneous, but we can make these assumptions under certain conditions. So the Agual, Alusani, Rami type curves, you can just refer to this as the Rami type curves, involves plotting the dimensionless pressure against dimensionless time. This type curve is useful for build-up test and for gas well test analysis. The peculiarities of this particular type curve is that each curve corresponds to a specific value of skin and wellbore storage. Of course, even though you must have a knowledge of this prior to your analysis. The McKinley type curve is used for characterizing damage or stimulation for a short-time test where wellbore storage effects distorts the data. The skin factor is not captured, rather a near well transmissibility term, that's the variability thickness product divided by viscosity is what is used. I'll go to the fourth one which I have here, which is the type curve where you have the plot of dimensionless pressure versus the ratio of dimensionless time to the square of dimensionless radius. This is basically used for the analysis of interference test, and you can calculate permeability and porosity from this. The type curve which I'll be using to demonstrate the functionality of type curves is the Gringertin type curve. For the Gringertin type curve, dimensionless pressure is plotted against the ratio of dimensionless time to dimensionless well-bus storage. And there's a correlating parameter which is defined by this term, which we'll see in the upcoming slide. It's useful for both drawdown and build-up tests where the early time data is dominated by well-bus storage. And this, of course, in the lecture material, I think I have something on the Rami curves, but I'm just going to focus on the Grigatin type curve in this video. So the type curve developed by Grigatin et al. In 1979 is based on the solutions to the diffusivity equation, modeling the flow of a slightly compressible liquid in a homogeneous actin formation. That's the underlying assumption. The initial condition is uniform pressure throughout the drainage area of the well. That's initial condition. The outer boundary condition specifies an infinite acting or unbounded reservoir, while the inner boundary condition is constant rates with well-bus storage and scale effect. So this just will take your mind back to the diffusivity equation, which we talked about earlier. Now, the initial and boundary conditions assumed for the solutions plotted on the Grigatin type curve are the same for the Rami type curve. It's just that in functionality, the Grigatin type curve is it's more amendable to use. For the Grigatin type curve, which I would show the next slide, dimensionless pressure is plotted on a log-log scale against the ratio of dimensionless time to dimensionless well-bore storage. The resulting curves characterized by dimensionless group, which is a product of dimensionless well-bore storage to the exponential of the double skin factor, represents different well conditions ranging from damaged wells to stimulated wells. So let's go into a few properties of the Grigatin type curve. As long as the well-bore unloading accounts for all the flow, and this is a period for which your test data is distorted or is influenced by well-bore effects during a drawdown test, or after flow accounts for 100% of the flow rate after shortening, a line having a slope equal to 1, I think I need to annotate this, a line having a slope equal to 1 will occur at the early times on a log-log plot. In dimensionless variables, the unit slope line has this property that the dimensionless pressure is equal to the ratio of dimensionless time to dimensionless well-bore storage. Or put this way, and let me reiterate again, that a line having a slope equal to 1 will occur at early times on a log-log plot. And then you see this. If you take the logarithm of both sides, you would have that the log of dimensionless pressure is equal to log of dimensionless time minus log of dimensionless well-bore storage. This relationship gives the characteristic signature of well-bore storage effects on well testing data, which indicates that the plot of dimensionless pressure versus dimensionless time on a log-log scale would yield a straight line of unit slope during the well-bore storage dominated period. And interestingly, this is the same thing whether we are talking about typical type curve and the Grigakin type curve, or which we see later, the pressure derivative curve. You have the typical signature is during the well-bore storage dominated period, if your well test data is plotted on a log scale, it would yield a slope, a unit slope, that's a slope of 1 during the well-bore storage dominated period. Now, since the dimensionless pressure is proportional to the pressure drop and the dimensionless time is proportional to the shortening time or the flowing time, depending on the nature of the test, it's convenient to plot the log of the pressure difference versus the log of time and observe where the plot has a slope of 1, has a slope of 1, has a slope of 1, has a slope of 1. Okay, I will address this portion. This unit slope observation is of major value in well test analysis. Now, so Grigatin modified the dimensionless pressure solution shown earlier to incorporate both well-bore storage and skin. And this is equation 40. This is actually this is the same equation we have for the solution to the diffusivity equation, the log solution. Of course, this is in lean form, and this was modified to include well-bore storage. So the figure TC2 shows that all the curves merge in the early time into a unit slope corresponding to pure well-bore storage flow. At the later time, with the end of well-bore dominated period, the curves correspond to infinite acting flow. And let me show you what I'm referring to as TC2. Okay, so this is TC2. And in TC2, you would see on the y-axis, you would see dimensionless pressure, while on the x-axis, you have the ratio of dimensionless time to dimensionless well-bore storage. So this is the well-bore storage dominated period. You see that all these curves, regardless of all these curves, they will converge to this unit slope at the very early times, and then the curves tend to go horizontal, and these curves you see here, where they intersect with the theoretical solutions, indicate the approximate start of the straight line. So these type curves help you differentiate, so you know that prior to this portion and this portion, depending on the solution, this is the well-bore storage dominated period, and from here, infinite acting flow develops. So the well-bore storage coefficient that C can be determined from any point. This USL, this subscript is unit slope on the unit slope line. Substituting the definition of dimensionless pressure, time, and well-bore storage for a slightly compressible fluid into D59, you would find out that the well-bore storage constant would give you this. This is the product of rate, formation volume factor, and then this is change in time, and then after last from the insertion of the test change in pressure. this taken from the unit slope line. And of course, the corresponding dimensionless well-bore storage coefficient can be obtained from this relationship. Now, let me just mention that from the test data, you would see that the test data primarily gives you pressure and time. So for the test data, you are not plotting the well-bore storage coefficient, but you see how it is obtained by using the Grigating type curves. So I've already shown you figure TC2. So, and then this has been illustrated before. So you would see how to use these equations in the following example. I think it's best understood that way. Whether it is, so I think I referred to this, but let me go into the example. Okay, prior to that, let me just mention this. So to obtain dimensional parameters of interest to you, like permeability, well-bore storage, skin, you will need to prepare your own test data on a log-log scale, and then displace the plot either vertically or horizontally. In the earlier days, it used to be done by hand, but now this is done using software. And the plot is displaced until you have the data lying at least closely fitting or exactly on one of the curves. And then from the match point, for the pressure match point, you can obtain the permeability. From the time match point, you get your well-bore storage. And then from the dimensionless characterizations group, you can now get your skin. As I mentioned, I will like to illustrate this data. Now, you would, for the type curves are basically designed for drawdown tests. However, to use them for build-up tests, you would need to use an equivalent time. Let me see, I'm not sure whether I have it here. Okay, I think I have that in an earlier slide. Let me just, okay, so this is equivalent time. So this is what, if you want to analyze build-up tests using type curves, whether it's the Rami or the Grigating type curves, you will need to calculate an equivalent shortening time. So you see this is, so the equivalent shortening time is the shortening time and then divided by 1 plus the ratio of the shortening time and the producing time. Of course, you know that the producing time prior to shortening is a constant. And of course, this changes with your data. So please take note. This is for our information. So I think this is a good time for me to go into the example. So the data summarized in table 4.1. Table 4.1 is actually one of the examples we used when I was trying to explain semi-log data analysis. So the data summarized in table 4.1 are from the build-up test of an oil well. Because the reservoir pressure is still above the bubble point, only oil is flowing in the reservoir, of course, so that's single phase flow. Estimate the effective permeability to oil the skin factor, the well-bore storage coefficient with the Grigatin type curve. In addition, analyze the data with the Horner semi-log plot method and compare your results. Known reservoir and well data, similar to when we did the conventional semi-log analysis, is provided here. So here you have the well-bore radius, the formation volume factor, reservoir thickness, viscosity, producing rate, porosity, compressibility factor. This is the well-bore flowing pressure just before shutting, and then this is flowing time, and then we have an average reservoir pressure reading. So to do this, and take note, even though this is for build-up test, this can equally be done for a drawdown test. In fact, I think in the tutorial set 2 I gave you, the question I gave was for a drawdown test, but the same thing could be done for the build-up test. So let's take it step by step. So the first thing, of course, because it's a build-up test, we have build-up test data, you cannot use delta t straight off. You need to find the equivalent time. So first is to plot delta p, which you can get from your data, as a function of the equivalent time on a log-log scale. And this is shown in figure TC3. Let me see. So figure table 4 is, let me see. Okay. So I was looking for that table. So here it is. This, what we have here with the dark points, these are the actual test data points. These are the actual test data points. The lines here, the curves here, are the theoretical solutions. And I'll come back to this. So to obtain the table, and I think before I continue the explanations, I think this is instructive. So this is oh no, this is for the Horner time. So sorry, I think I'm missing a table. I think I can supply it in the material I'll be posting to the LMS. I think the basic thing is that is on the calculation of the equivalent time, and remember the equivalent time is the shutting time as a ratio of 1 plus the shutting time over the producing time, and we have everything that we need for that. So that's the first step. So the first step would be to prepare that plot on a log-log scale. Now, the next thing would be to identify the data that fall on the unit slope line so that we can estimate well-bore storage coefficient and then the dimensionless well-bore storage coefficient. Now, here, the coordinates are given for the change in pressure, 40.29 psi, and the equivalent time, 0.001 hours. So the point is, how did we get this? So let me